Hi everyone, today we are going to present our masterclass, how to produce lithium battery cell like this. So in 5 episodes, we are going to describe how to produce lithium battery cell components, how the manufacturing equipment looks like, and which are the process challenges that describe the gigafactories worldwide. So we are going to discuss how to produce these battery cells like Tesla or Power Cell or prismatic cell, even including the blade cells. And we go through each single process technologies and we describe all the challenges. This course can be the right one to allow you to increase your knowledge in lithium battery manufacturing and at the same time be fully prepared for the job interview for all other gigafactories and players if you want to join in the lithium battery manufacturing industry. So stay tuned, subscribe to our channels and enjoy.
So the main topics that we are going to cover today are how a lithium battery works, okay, just a very quick overview, which are the components and material that compose the lithium ion cell, lithium battery cell, a quick overview about the market trend and overview about the next coming projects, okay, and then we are going in deep dive into the format type, their application, the manufacturing process, especially for the battery cell, okay? And the technology used for the manufacturing of lithium-ion cell and the equipment used, the equipment maker, which are the main equipment maker, which are the challenges in terms of manufacturing, in terms of process, and even an overview about the quality controls, okay? With me, I have some samples, okay, of some batteries of my customer. For sure, I cannot mention the name of the customers related to the battery cell that I have here with me, but this will help me to explain you some details. Okay, so right now, as you know, the world is facing a transition, okay, in terms of energy. Many companies and startups are investing in Europe, United States, and even in Asia. But in Asia, the business is already established. Okay, the most expert battery manufacturers and equipment maker are sitting in Asia. Okay, and they are spreading their business in Europe and United States, starting from 2012, 2014. But right now, many new companies now are joining the business. And the problem of Europe and the United States is that the supply chain is very weak, okay, compared to Asia. Very weak, and that means that there's no strong network in terms of raw material suppliers, in terms of equipment suppliers, and even there is a lack of skills, okay? And this is a huge problem for who want to start this business. And this is the reason why I'm here, okay, to try to increase the knowledge, to spread the knowledge, to support the companies. And yeah, if we go ahead, we say that in terms of the market trends and main application, the lithium batteries are not used just for the electric cars, the electric vehicle, but are used even for electronic device, for power tools, for light vehicles like e-bike, e-scooter, and so on, that our Indian participant knows very well, this, since e-scooter is very famous in Asia, and the e-bus, but even energy storage. For sure, there's a lot of interest in the automotive field, okay? This is the reason why the lithium batteries became so popular during the last years, but believe me, there are even a lot of investment in the energy storage field. If we, this is a very, I think, very complete overview about how the market demands increase and how it's split between the main application. No? As you can see on the let me change. Okay, as you can see on the bottom side, the main application will be related to the automotive business. Okay, for BV, MHEV, FHEV, PHEV, and even commercial vehicle. And a very small part is related to the consumer electronic device and others. And then a big portion is increasing in terms of energy storage. The reason why the the size, okay, of demand for the EV is bigger than, for example, the energy storage and even the electronic device is related to the average size of the battery pack for EV vehicle compared to the electronic device. Okay, I mean, in our smartphone, we're just one battery cell, okay, at 5 ampere hour, 7 ampere hour, something like that. In EV vehicle, we have battery pack from 40 kilowatt hours to 100 kilowatt hours, okay? And even if the quantity of electronic device is huge, there's no comparison between the EV market with the electronic device. Looking at the region, for sure, the China represent the main area, okay, in terms of lithium battery capacity, okay. China, as you know, has an internal market, okay, to feed, but even already existing a very huge manufacturing company, like CATL, BYD, Lishan, and even Wangxiang, and so on. And in the European Union, the business is going to increase very, very quick. As you see, in 2019, the European production capacity represented the 6%. In 2024, we're going to represent the 15%, and then increase to 16% in 2029. For sure, these are related percentage, but if we check the overall capacity, the trend is increasing very, very quick. If the total capacity worldwide was, based on this study, 460 gigawatt hour per year in 2019, is going to be 1,500 gigawatt hour per year in 2024. So at least 4 times bigger in just 5 years. And then is going to be over the 2,000 gigawatt hour per year at the end of the decade, okay? These are just estimation, okay, projection. For sure, right now we are in a very particular phase, okay, where we have some constraints, okay, to develop the lithium battery cell and even establish the factories, okay. Europe is facing the energy crisis, where the electrical energy is very, very expensive. This is limiting the investment, okay, in the last year. So the projections and the benchmark are going to be adjusted, okay, in the next months. Here a very, very general overview about the incoming projects in Europe. As you can see, Germany is going to be one of the main places, okay, for the next gigafactories. Even the Scandinavian area is going to get some factories, thanks to Norvolt, Freer, Moron, and even Panasonic, that is going to announce the factory. But again, the Norway is going to be one of the best places, since the energy cost is very, very low, okay, compared to the other area. Indeed, some companies in Germany that planned to invest a lot of money now in the scale up of their current production plant decided recently to move the investment to other worldwide area, okay, because the energy cost is too much expensive to have a return of investment in very short time. I mean, with the current state of art in terms of energy costs and so on. So yeah, again, this moment is very, very particular, and some limitations are going, okay, are coming. And even many startups and companies are facing the issues that I mentioned to you before. So the lack of competencies, the lack of experience of the manpowers, and even of the supply chain. Okay. So if right now you are going to see in LinkedIn, in the websites and so on, that maybe many factories are going to establish production in very short time. Yeah, I mean, is very tight schedule. Usually you need to multiply by 2 or 3 times, no, the announced schedule. For example, I participate to the startup of the first gigafactory in Europe for LG, and their plan was to achieve a steady production condition in 1 year. I mean, I'm talking about Wrocław, okay? But we reach a steady condition by beginning of 2020, so with the 1 year and a half delay. Okay, and LG is one of the most expert player, no, in this business. Okay, we can move on. This is a recent study that we made personally. We try to understand how I mean, what is the trend, no, in terms of gigafactory projects, okay, in the next years. And based on the announcement, based on the official plan, most of the gigafactory should start the production starting from 2024, okay, till 2026. And the factory, the average size of the first step factory is between 1 to 10 gigawatt hour per year. That, believe me, is quite huge plant, okay, with many production lines. But the ramp up phase foreseen to reach between 30 to 50 gigawatt hour per year, okay. As mentioned before, one of the key elements now to establish the factories is the equipment supply chain, okay. And if the battery production is going to increase, even the market for lithium for the equipment, okay, is going to increase. As you can see, the trend is going to increase very, very, very quick, and the investments are in all area, okay, for the battery manufacturing. So in electro manufacturing, cell assembly, cell finishing, that represent the three main area of the lithium battery production, okay. For in Europe, we need to say that most of the players are investing in electro manufacturing business and even in cell assembly business. From equipment point of view, cell finishing is mainly represented by Asian player right now, okay. And in Europe, there's no many companies that are going to invest in equipment for cell finishing. For region, again, as you can see, China represents the main part of the supply chain for battery equipment, but Europe is increasing very, very, very quick. Just to think that in 2020, Europe represented the 0.1, okay, in terms of billion of euro, okay, of sales. In 2025 is going to represent 3.2 billions of euro. So 32 times more in just 5 years, okay? And the target is going to double by end of 2030, okay? So this means that the West market, in terms of even United States and Europe, are investing a lot, not just in the battery manufacturing, but even in the equipment manufacturing for batteries. Okay, so give me 1 second, that some people are asking me why they're not, they cannot join. Okay, So what is a lithium battery cell? Okay, lithium battery cell is we can say is a device, okay, that is able to storage the energy. Mainly the lithium battery cell is composed by some elements that are anodes, cathodes, separator, and electrolyte. Okay, these are the main components. We can include even the case, okay, but we can start with the anode. Anode is a copper thin foil covered on both sides by active material. For cathode, active material is mainly composed by graphite that could be natural or synthetic, and or graphite with silicon oxides, okay, compounds. This is a new generation of anode. Later on, we are going to have some deep discussion about that. Then we have the cathode. Okay, the cathode is aluminum foil covered on both sides by active material that is composed by metal oxides. The most famous are the chemical composition NMC, that means nickel, manganese, and cobalt oxides mixed with the lithium compounds. And an alternative is represented by the lithium iron phosphate, okay, that doesn't contain any nickel, cobalt, and manganese compound, but just iron phosphate compound. And the properties are quite different from the NMC compounds, but even the price. Even for the cathode, we are going to have a deep dive later on. The third element is the separator. The separator is placed between the anode and the cathode, okay, represent the electrical insulation of the battery cell, but the separator has a control porosity, okay, so it's a polymer film with a very controlled porosity. The porosity is in the order of nanometer. It's very, very small. And this allowed the lithium ion diffusion, okay, from the cathode to the anode and vice versa. So thanks to the separators, again, the lithium ion can move from cathode to anode during the charging cycle, and from the anode to cathode during the discharging cycle, okay? The lithium ions comes from the electrolyte, okay? The electrolyte is basically lithium salts dissolved in aromatic compounds. So is very toxic compound. And the electrolyte, as mentioned before, the lithium salt dissolved in the organic compounds, okay? And then the lithium salt will be transformed in ions, and the ions are able to move from the cathode to anode and vice versa during the charging and discharging. So these are the main elements that compose the battery cell, okay? And here there are, okay, I need to move this here. Here we have some chemical composition, no, of the battery cell. In the beginning, it was lead acid battery cell. Then the market moved to nickel cadmium battery cell. As you can see, the reason was higher energy density and higher working life cycles. Okay. Then the trend was to move very quickly to nickel-based battery and lithium-based battery. Okay, the first lithium-based battery was the lithium cobalt oxide. Okay, established, commercialized in starting from 1992, where the energy density was quite good. I mean, we are talking about 150 watt-hour per kilograms, and with a modest working life cycle, okay, just 800 cycles. Then the research move into different compounds, adding manganese and nickel to the lithium formula. And thanks to that, the batteries were able to reach higher energy density, but even longer working life, okay? For example, as mentioned before, right now, the most established chemistry are this one, the lithium iron phosphate, the lithium nickel manganese cobalt oxide. The first one is called LFP. The second one is called NMC. The main difference between them is the functional voltage is lower for lithium iron phosphate, is higher for the NMC, and even the energy density is higher for NMC. To the other side, the LFP is much more available in terms of raw materials, but it is even cheaper. Okay, so there is a compromise between cost, availability, and performance between LFP and NMC. In terms of working life cycles, the LFP guarantee a longer working life, okay, compared to the NMC. And usually there are different philosophy now to use NMC over LFP and vice versa. Many Chinese makers are using LFP for prismatic and pouch cell. Okay, later on we are going to explain what is a prismatic cell, for example. In Europe and Korea, the battery makers prefer the NMC. Okay, the LFP is able even to work in a wider range of temperature. So due to this feature, since for some application is not needed a very high energy density, especially for not automotive applications. So for example, for the energy storage application, is not needed a high energy density because the weight is not a KPI, is not a very important KPI. The LFP is can be used even so for the energy storage application because they are very long working life cycles, very safe working range in terms of temperature, and even if the battery pack is bigger compared to NMC, nobody cares. I mean, it's not a huge problem, okay? But is a huge problem for the EV application because we have space constraint and weight constraints in EV application. This is the main reason why NMC battery cell are used for EV application. But there are some exceptions. For example, for BYD and other Chinese makers that use the battery cell, LFP battery cell for EV application because they found a way to increase the energy density in the overall battery pack. Okay, so they get rid of the problem of lower energy density. Okay, what is the current state of art? Okay, the current state of art, as mentioned before, is LFP and two different type of NMC. Here there is a mistake, sorry. One is high manganese NMC and one is high nickel NMC. The price, as you can see, is higher for high nickel cell, lower for LFP. The energy, okay, inside each single cell is very high for high nickel content and very low for LFP. As mentioned before, there's a huge difference in terms of life cycle, okay? And even as mentioned before, the safety is higher for LFP, even due to the higher, wider working range in terms of temperature. The recycle value is lower for LFP. The reason why is the raw materials are very, very cheap compared to NMC precursor compounds. That means that there's not a lot of business, okay, for the LFP recycling. And because, yeah, the value of the single elements are not so high, okay. In terms of toxicity, for sure, LFP have a very low degree of toxicity over the NMC battery cell. The reason why LFP battery compounds come from some very common material, okay, and precursor like iron ore, iron sulfate, iron phosphate that could be that are used even in the food industry, no, sometimes. For the NMC, we cannot say the same because all the compounds that comes from cobalt, nickel, and manganese have a very high toxicity level for the human body. Okay. Another very important KPI is the material availability. No, iron is very, very, very available in a huge quantity all around the world, worldwide. Nickel and manganese don't have the same availability. Okay. Sorry, but give me 1 second. Okay. Um, Sorry, but some people understand just right now that they needed to purchase the masterclass to join, and right now they are writing to me continuously on LinkedIn. I don't know. Anyway, there are existing different type of battery cell. Okay, cylindrical. I don't know if you see my camera. This is cylindrical batteries. Okay, cylindrical cell, and here there is the cylindrical cell in the case. Then there is prismatic metal can cell that are bigger and pouch. For example, this is a battery cell that are going to be in metal can housing. Okay, is a prismatic. If we compare the dimension between these two one, you can see that the prismatic one is bigger, no, than the cylindrical one. And for pouch, we have this kind of cell. Sorry if it's damaged, but I don't have a good one that is going to be applied in EV application. Okay. Unfortunately, I don't have any coin cell, but anyway, maybe next week I can send to you some pictures of coin cell. Just to explain to you, the coin cell has the diameter comparable to the inner diameter of this cylindrical cell. So we are talking about a cell with the 4 millimeters of diameters. Okay. Okay. So let's start to discuss about the cathode. Okay. The cathode is one of the main materials mentioned before for the battery cell. As you can see on the left side of the screen, there is a SEM microscope picture that show a cross section of cathode material. You can see in the middle the aluminum foil. Okay, on lower side some particles coating, and upper side particles coating as well. So we're talking about very thin aluminum foil. Usually the thickness of aluminum foil vary from 10 to 20 microns. Okay, depends mostly on the application. And the coating thickness could vary from, we can say 30 to 80 microns for each side. Okay, so we can say that this is 60 microns, 10 microns, and again 60 microns. So in total, we're talking about 130, 160 microns thickness electrode. There are some cases where the battery makers are able to produce very thick cathode material. This for sure have some limitation for some manufacturing process, but could be a very positive things. So this can bring many benefits because increase even the capacity of the battery. What to say? Yeah, just to think, okay, this is cylindrical cell, okay. For sure, if we think that this cylindrical cell is obtained winding the element all around the spindle, we see that a very thick cathode or anode could be a problem because the maximum radius, okay, curvature radius that is allowed for a very thick material increase with the thickness of material. That means that if we want to produce a very small battery cell, we cannot use very thick electrodes. Instead, if we're going to use a prismatic cell or a pouch cell where the layers inside the cells are stacked. Okay, so there are some sheets of electrodes that are stacked one to each other. There's no problem in terms of thickness, okay, because we don't bend the electrodes, okay, especially once the cell is inserted inside the case. In Yeah, the cathode material as the anode material is produced in a manufacturing line that is called electrode manufacturing line that we are going to see later on, and is composed by multiple steps. Okay. In terms of cathode technology, the current state of art provides many different type of cathode. Okay. If we wanted to grade or to rank, okay, the cathode material, we need to use the following KPIs. So the chemical composition is one of the KPIs, the energy density, the working life, the value chain, and even the application affect the mentioned above choices. Okay. The chemical composition for sure affect many aspects. Okay, because the chemical composition could affect, as mentioned before, the availability, okay, of the raw materials. So, and even the number of potential suppliers that can provide you, okay, the chemical compounds. Even the chemical composition affect a little bit the manufacturing process or the complexity of the manufacturing process. For example, if we want to produce LFP cathodes, okay, we need to consider that LFP is hygroscopic, okay, and is very hygroscopic compared to NMC cathode. This means that if we have some humidity, okay, in the environment, in the production environment, or we have some moisture level, the LFP cathode tends to absorb the water, okay, and this makes difficult to dry up the electrode later on, okay, and this for sure will affect badly the battery cell performance. So just to go ahead with this example, that means that for LFP cathode material, the battery maker needs to foresee a dry room area, even for the electro manufacturing area. But this is not needed for the NMC cathode. So the chemical composition in this case affects the capital investment, because in one case, the battery maker needs to foresee a control environment in the production and dry environment. In the other case, the battery maker don't have so many constraints, no, in terms of humidity level in the production environment. The energy density is another very important KPI, because this affects the energy amount that can be stored in a single cell, okay, in a single cell. And based on the application, that means that this affects even the number of cells in the battery pack to achieve the same performance, okay? So if the energy density is low, okay, I mean, if we have two different levels of energy density, okay, one is I don't know, 160 milliampere per hour on grams, and another one is 200. For sure, the lower energy density require more battery cell inside the battery pack. Okay, so more battery cell in the battery pack means more connection, more process, more elements to controls, more sensors. So at the end, even more cost, maybe, but for sure more effort for the manufacturing. Okay. And in terms of production capacity for the production plants, that means that if we want to achieve the same production capacity in terms of gigawatt hour per year, we need to produce more battery cell. Okay, so if we have very high energy density cathode, we need to, with the same shape of battery cell, with the same dimension, higher energy density means less cell produced in 1 year to achieve the same production capacity. The working life is another KPI because depends on the application as well, okay? The value chain already, again, is a very important KPI because the value chain affect everything in terms of logistic, location of the production plant, cost, and even risk, okay, in terms of supply. Another aspect to consider is the value chain affect even the recycling business, okay? As mentioned before, there's very, very poor interest to recycle the LFP batteries, but many players are investing to recycling the NMC batteries, okay? Because in this way they can recover not just the lithium, but even the cobalt, the manganese, and the nickel, okay? That represent a very big portion of the overall cost of the cathode material. And then for sure, the application. I mean, the application is a result of the mentioned above KPIs. As you can see on the right side of the screen, this is an example for 1865 battery, cylindrical battery cell that are a little bit smaller than this one, okay? The cathode active material is the most expensive components inside the cell, okay? And this is true for LFP, but even for NMC. As you can see here, the cost for each cell seems higher now for LFP than for NMC. The reason is if we compare the cell with the same, okay, energy density, or capacity, sorry, with the same capacity, at the end we need more LFP than NMC, so at the end the cost increase. In terms of, again, cathode technology, we can have another deep dive. This is a resume of what we have seen before. We can start to rank the composition, okay, the chemical composition based on the energy density, okay. The most famous, the most common batteries are NMC. As you can see, the energy density moved from 140 to 220, okay. Even the NCA with aluminum have a very high energy density. The LFP is in the middle, no, of the NMC range. Another very different KPI is the voltage, sorry, the nominal voltage. That is 3.7 for the NMC and NCA, and it's just 3.2 for LFP. That means that if we want to understand the energy content of each single cell, okay, that is obtained multiplying the energy density by the voltage, okay. The LFP as with the, I mean, considering the same cell in terms of dimension, in terms of shape, the LFP battery cell contain less energy than NMC, okay? So with a very quick calculation, if we consider 220 milliampere hours on grams by 3.7, we are talking about 814 milliwatt hour, okay, on grams, 813. If we consider the LFP, we are talking about 540, okay? So we can say that is 40% less, okay? 30 or 40% less in average. The other KPIs, as mentioned before, is the stability, very high for LFP. The reason is very wide temperature range, working in very wide temperature range, long life for LFP and medium life for NMC. But the LFP is very difficult to obtain in terms of active material because I mean, the working window is very small now compared to NMC. But as you can see on the in the last row, in terms of usability, NMC and LFP are the main technologies in terms of cathode that are using currently in EV energy storage and electronic device. Yeah, this is a how to say, a detail about what I mentioned before in terms of temperature range. There is a phenomena in the lithium batteries that is called thermal runaway. Okay, when some failures occur inside the battery cell, the temperature increases very, very quickly. We're talking about hundreds of degrees, Celsius degrees in a very short time. So in even less than 1 second. And the thermal runaway occur for NMC at 200 degrees, okay, more or less. But for LFP, this temperature range is very, very high, okay? That means that the LFP is able to survive even in very extreme condition, okay? And indeed, in some worldwide area, it's preferred to use LFP than NMC because maybe the application foreseen to use the battery at very high temperature, okay? And this is not possible for NMC, for example. This kind of slide represent a good overview, okay, of the combination of the KPI in terms of cost, fast charge, safety, specific energy, specific power, and lifespan, okay? As you can see, the NMC and the NCA are the ones that can cover more or less in a good way all the KPIs. The LFP has many advantages in terms of fast charge compared to NMC, and even in terms of safety, for the reason that I mentioned before, and even in terms of lifespan, okay? In terms of cost, there is no difference because, again, if we need to compare exactly the same system, now in terms of kilowatt hour, we need more LFP than NMC. So at the end, even if 1 gram of LFP costs less than 1 gram of NMC, for a battery pack, you need more LFP. So at the end, the price, the cost is more or less the same. In the last years, there is a new chemistry that I think is the chemistry of the future for lithium-ion batteries, okay, excluding solid-state batteries and so on. That is the LMFP. This is here is called LFMP, but you can find it even in LMFP. So it's a lithium iron phosphate chemistry with manganese inside. What is the difference between LFP and LMFP? The main difference is the manganese increase the energy density, okay, but even increase the operating voltage. Okay, so we have the same energy, we have more energy in the same batteries because we have higher energy density in the coating, but we have even higher operating voltage. Okay, and at the end, this increases the watt hour per single cell. Okay, and at the same time, the LMP keep the advantage of LFP in terms of material availability, in terms of cost, in terms of safety, in terms of fast charge, and so on. So this is the reason why many battery makers are moving from NMC to LMFP, especially due to the recent geopolitical situation that trigger now, and an increasing of the price for nickel and manganese, very, very hard, very strong. Many battery makers decide to move to LMP. Okay. Who are the cathode maker? Okay. The main cathode maker are Umicore, POSCO, LG Chem, LAF, and Cosmo. Okay. As you can see, their investment are very huge. The trend is to move from 180 1,000 tons per year to almost 900,000. Okay, so we're talking about six, 5 times more in just 5 years. Okay, the reason is since the production capacity in terms of lithium battery increase, even the rest of supply chain need to increase their production capacity. So this is valid for the cathode, but even for the anode. Okay. And there are different strategies in the market, we can say. There are companies that are producing the active material internally, okay, starting from precursor. But there are even battery makers that prefer to buy the active material from other companies, okay? So the difference is huge, okay? Because again, if you have integrated manufacturing system, even for raw material, you can control better the quality. You don't have any risk in terms of supply chain, or even you can minimize the risk in terms of supply chain and even delivery time. You can reduce the cost, so increase the profit, okay? But not everyone have the capability in terms of money, in terms of knowledge, to include the active material manufacturing inside their production plant. One of the example of company that integrate the active material production just partially is LG Chem, that is one of the biggest player in the battery business. But if we talk about the current European and American startup, most of them are going to purchase the active material from a third-party supplier. Here, okay, before we show the expansion plan for the cathode material maker, and here we have an overview for the cathode material market demand, okay? As you can see, the market demand is very, very huge and is higher compared to the expansion plan that we have seen before, okay? So if we consider that in terms of demand, the market in 2025 is requesting more than 2 million tons. And here in 2025, we're talking about 1 million tons. I think there is a huge difference, okay? The data should be correct since we got this graph, this data from the same study, okay? So that means that yeah, the demand is increasing very, very, very quickly, and the supply chain is not ready to feed the entire downstream. This could be a problem in the future, and this could be a constraint and a bottleneck for further expansion plan of the battery makers. But this is the current state of art, okay? Recently, we studied many articles, and yeah, quite everyone is going to invest in the lithium battery cell, lithium battery pack production, but just few are investing in the supply chain regarding the raw material and the precursor compounds. And then another problem is the material availability, okay? Some components come from mines that are located in a specific area, and so for some elements there is kind of monopoly, okay, or some kind of cartel. But yeah, this is the current state of art. So the trend is to move to more available material like LFP and so on. Indeed, as you can see, this study is from 2020, so it's not super recent. In 2020, the analysts already foreseen that the LFP demand was moving from very small quantity, 23K tons per year, till 2030 to 1,134K tons. Okay, so the trend is going up, and I think if we check the latest analysis in the latest report, we see that the LFP will become the main chemistry now for lithium-ion batteries, or I mean, variation of LFP.